Where's Mr. Bailey at? Okay. This is too big and doesn't need to be over here. All the trash man. Y'all probably, like, I don't think I've ever told you all this, but my dad, when I was younger, used to be a trash man. He drove the big BFI truck. I don't think he really ever did residential, but he drive the big truck that has the like forks that picks up the big trash dumpsters and dumps them. And I'm not ashamed to say he always found really cool stuff in the trash. And I had like trash gifts pretty often. Like my first Louisville Slugger baseball bat came out of the trash. He found this awesome like little like miniature jukebox. I guess like I know that he didn't like dig through the trash for stuff. So I guess if you think you have something cool, but you're like you got to throw it away, but you don't really want to throw it away, you set it next to the trash. And then I remember one time he said they had a big issue because this is sad, but I think this like old police officer passed away, and his wife like threw away all of his guns and ammo, and you can't like put like boxes and boxes of ammo in the back of a trash truck and like compact them because there's going to be issues. And so there was like a big hubbub about it. But yeah, my dad used to be a trash truck driver. Now retired. Not from he was like a driver my entire life. He worked for like pool companies, like hauling the dirt out when they dug a pool. He drove an 18-wheeler for a while. He was always a truck driver. Yeah, that's my dad. Okay, little home story for you as your news story today. Let's see. We're picking up here. We're on slide 44 of 63. So we have less than 20 slides, and I think we can get it done today. So we left off yesterday with the two different types of sedimentary rocks. We have detrital and we have chemical. And the main difference between these are detrital, and I told you to kind of think of the word detritus, like little pieces falling off. Detrital rocks form from solid particles of weathered from other rocks. Sorry, it's a little early. So it's literally going to be broken pieces of other types of rocks, whether they're igneous or sedimentary or metamorphic. It's the broken down pieces, and you can see that. So like a sandstone is going to be like a detrital rock. Chemical and biochemical sedimentary rocks are going to be things that have been dissolved away in water. The water goes somewhere else, and either the ions come out of solution by just attaching themselves to something else, kind of like a stalactite or a stalagmite. Those are sedimentary rocks. Or the water evaporates away. You get like a salt bed or a gypsum bed or something, like the Great Salt Lake. The Great Salt Flats. There you go. So that used to be a salt lake, and then all the water evaporated away, and it left the salt behind, and those are chemical sedimentary rocks. So detrital rocks contain a wide variety of minerals and rock fragments. A lot of clay and quartz are most common. Here are your detrital rocks. And so again, unlike minerals where there's lots and lots and lots of minerals, there are only 6 detrital sedimentary rocks. There's going to be some more on the other side for chemical, but not a whole lot more. So your 6 detrital sedimentary rocks are essentially organized by particle size. So we go from large particles down to small particles. And in particular, we start with the 2 largest, which are coarse grained, which is over 2 millimeters. So the gravel is what's making up the pieces of these rocks. And again, I told you that sedimentary rocks kind of tell Earth's history and what was going on. And so each of these rocks also has a very specific place that they form. If you're getting big pieces of rock compressed and cemented together, this is going to be very close to the mountains, oftentimes in a river. These are usually considered river rocks. They can happen outside of rivers, but it's going to be somewhat close to the source because the pieces are large. They didn't travel very far from where they broke off of. So these are probably going to be somewhere close to a mountain range or a rock outcrop or somewhere where the original pieces broke off from. So we have two different rocks here. We have conglomerate, which you may have heard this term in business class if you've taken business class. A conglomerate in a business is a company that owns lots of different companies. So they've kind of bought different companies that do different things. That is a conglomerate. And a rock, it's kind of the same thing. It's a rock that has lots of different little rocks inside of it. And then you have breccia, which I believe, I don't know if it's Italian or it sounds Italian. It could be Latin or something like that. But breccia essentially stands for broken. And so these are very similar rocks. The only difference between the two is conglomerate has rounded particles. And so it's hard to see in this picture, but all the little spots in here are nice and round. They may not be perfectly circle, but there's no sharp edges. They're rounded off. They've tumbled down a hill and had all the sharp edges broken off, or they were in a river and have had kind of the round edges or the sharp edges eroded away, weathered away, sorry. Where a breccia has very angular particles, and you can kind of see these look almost like freshly broken. There's lots of sharp edges and different angles going on here. And so particle size is the same. They're both gravel, but the different names refer to the different shape of the particles. Is it rounded? Is it angular? So these are the largest size particles. Then you go down to medium, and medium is going to be your sand size particles. And we essentially have two different sandstones in a way. One of them is your normal sandstone. It looks like your sand that came right off of a beach. And so it's that nice white tan kind of color that looks what we all recognize as beach sand. The other one is going to be Arcos. This is a little bit more rare because these particles, while they're the same size, about 1/16 to 2 millimeters, they come more from like your granite kind of area. So you can see that they're darker in color. You have a little bit of lighter colored mixed in. It's going to feel like sandstone. The size is going to be similar to sandstone. It just doesn't have that colored look. And so it's going to have a different mineral constituency, which we're not really concerned about. We don't really need to know what kind of minerals are in it at this point. But you can clearly see the difference between a sandstone and an Arcos here, even though they should have a same feel and mineral size or grain size. So we go from coarse to medium, now to fine. Fine is going to be about 1/16 down to 1/256 millimeter. So these can get really small. And if this were not incorporated into a rock, so we've talked about gravel, we've talked about sand. If this weren't incorporated into a rock, it would be considered silt. So silt is pretty fine. And so this is a pretty easy name to remember. It's just siltstone. And same thing down here. If you go very fine, less than 1/256 millimeter, you get down into clay particles. And if you've has anybody ever like felt clay? Like, yeah. When you feel clay, even if it's like wet clay, you don't feel any like pieces inside. It's just very smooth, very, very fine. And so if you have clay-sized particles, you get this mudstone or a shale. And we've kind of heard the term shale around here because the oil and gas industry. Shale is actually where we get a lot of our natural gas from in the Texas area. So in the field, it's kind of hard to tell the difference between these because, your ability to tell the difference between just larger than 1/256 and smaller than 1/256 millimeter is pretty limited. This is the time where I've probably mentioned this in a previous class. You could like bite off a piece of the rock, maybe not bite it too hard. You don't want to hurt your teeth. But if you can get like a couple crumblings of the rock, and it's going to sound gross, put them in your mouth, kind of crunch them with your teeth a little bit. If you feel crunchy stuff in your teeth, it's a siltstone because you will be able to feel the size of the grains. If you kind of crunch it in your teeth and there's no crunchiness, it's just like mud in your teeth kind of, it's going to be a mudstone or a shale because the particles are so small, you just don't get that grit in between your teeth. It's just not big enough to really feel it as you're kind of chewing on it a little bit. Sounds gross to chew on rocks, but really when you do it, it's not too bad. I mean, hopefully you pick one that hasn't been like peed on by an animal or something, or isn't like right from the middle of the walking path. You're way out in nature. Maybe it's not too bad. But yeah, I've done it a couple times before. Got to do what you got to do to identify your rocks and get a good grade. So then we move on to chemical rocks. So detrital is going to be broken up pieces of other rocks, and they kind of go through that with the different sizes here. Your larger pieces, your medium pieces, and then your fine pieces. So chemicals going to work differently. You have to have water kind of dissolve other rocks away. And so when the water dissolves it away, it's going to carry these ions in itself until it gets to a different area, whether that's a cave or a lake bed or some kind of area where it can kind of stop and these ions can come out of solution. So your solid material, which will end up being your sedimentary rock, precipitates to form chemical sediments. So their example is salt left behind when a saltwater lake evaporates, like I mentioned, the Great Salt Flats, or minerals precipitated by organisms. So in the ocean, you have lots of little shelled creatures. There are some things like hermit crabs, which take other things' shells, but the shells have to come from somewhere, right? And so these creatures take calcium carbonate out of the water column. It's dissolved into the water in the same way that salt is dissolved into ocean water. And they take the calcium carbonate out of the water column, process it through their body, and they build their shell with it in a natural process. And so those shells become, once they become part of the rock cycle, become a chemical rock or a biochemical sediment. So they talk about shells and hard parts. Limestone is composed of calcium carbonate. Nearly 90% of that is formed by organisms. So when you see the white rocks around here in everybody's driveways, or just out in a field if you happen to be hiking or something, know that most of that white rock comes from shells and hard parts, meaning bones, of ocean organisms, and that for a decent portion of Texas history, it was mostly underwater in a fairly deep ocean, an inland ocean. So times have changed, but you never know. If something catastrophic happens, we might all have to move to a different state. Probably not in our lifetime. That would be ridiculous. But yes, these are the cliffs, the white chalk cliffs, massive white chalk cliffs. I don't know if these are actually them. They're famous cliffs. These might be them. The Cliffs of Dover, which I believe is in Ireland. Now I have to look this up real quick. But they're huge white chalk cliffs, and all that chalk was pretty much the same as we used to use chalk for our boards, are from these organisms, which are called coccolithophores. There's the name right there, coccolithophores. Go back. I just want to Google this real quick to make sure that I'm not being crazy.
It could be the cliffs in England or France because there are some that look very similar.
Yeah. Let's see. And yeah, Cliffs of Dover is the song. Yeah, it's going to be something like this. It could be the ones in France. You could probably find it in your book pretty easily, and I bet it's written down there. As Tanner pointed out to me. But yes, these are white chalk cliffs. And when we say chalk, we literally mean chalk that we used to use for chalkboards. Now, you probably can find chalk that's more industrially made instead of mined from places like this. But this is where we get our chalk from, and it's tiny little microscopic organisms called coccolithophores, and they make these really intricate pieces for their skeletal structure. And so you can see kind of the very intricate shapes that they use to kind of build their round soccer ball kind of shape. These are very, very small. They have the head of a needle here. And so this is probably done with like a scanning electron microscope, looking at the detail that they have down there. Yes, it was. See, I guessed right. Scanning electron microscope. And I've kind of lectured over this several times already. So not this year, but in previous years. So sometimes you remember things. But yes, all this again is deep ocean rock. So anytime you see limestone or a white rock like this, almost all of those circumstances, it's going to indicate that At some point in time in the past, this was covered up with quite a bit of water, and this would have been a deep ocean environment. So they're going to go over some names of these. I guess I'll go over them first, and then we can look at some pictures to kind of help you solidify that in your mind. This is a weird word. We've already talked about chalk. Chalk is made from the hard parts of microscopic organisms, and you should be able to kind of tell chalk when you see it. When you get it in your hands, you're like, this is chalk. Coquina is the word for this. Coquina. This is basically a rock that looks like it's just a bunch of shells glued together. You can see that they're shells. They're not broken down into small pieces. It's just a bunch of shells kind of glued together like it came right off of the beach. That is coquina. Travertine is inorganic limestone that forms in caves. It's going to be a white rock. It's going to be a little bit more solid, not as like crumbly and soft as chalk. Because it's a cave rock, it's kind of formed almost in the way like a stalactite and stalagmite. A lot of depositing over the same kind of material. And then you get chert and flint and jasper and agate. These are all microcrystalline quartz. And so chert nodules are actually also something that they're probably more commonly used for, sorry, what am I looking for? Your arrowheads and your different types of stone weaponry and stuff. Because while obsidian works really great, is there any like volcanic obsidian around here in Texas or in Oklahoma? No. And so unless you happen to live by one of those volcanoes, your ability to get obsidian is not going to be very high. And so chert, being based off of microcrystalline quartz is kind of everywhere. This is going to be more available for your arrowheads and stuff like that. And so that's probably a little bit more common. Flint, we're all familiar with flint and its ability to start fire in historical context. And then jasper and agate are really just two kind of colloquial names for the same kind of material. A lot of people carve these into little figurines and old like chess pieces. The pieces would be jasper or agate. And so it's all kind of different names for the same thing. Maybe a little bit different color and a little bit different consistency. But it's all quartz, and because of the way that it comes out of solution of the water, it's called microcrystalline because there's not any big crystals. They're just really like microscopic crystals. So it kind of has a uniform feel and texture. Then you have salt and gypsum. These are going to be your evaporates. So you have to have some salty water or water that has a lot of gypsum dissolved in it, and then the water has to evaporate, and what's left over is the salt or the gypsum. And then we get to coal. Know that coal and oil, like to kind of explain it, I guess, I don't know why we did this. I didn't do it. We kind of told ourselves, and this isn't like me putting anything on y'all. Y'all were told this. I was told this too. That oil and gas and coal come from dinosaur bones. And that is like objectively false. They come from that era in a way, but there were never anywhere close to enough dinosaurs to create that much material. And that's not the chemical processes don't work out in that way. And so while it does come from that era back when there were dinosaurs and those time periods, coal and petroleum, oil, natural gas, they come from more plant matter than organic meat matter in a way. And so it's not from dinosaur bones. It's not from dead dinosaurs. It's from plants in that era. Lots and lots and lots of plants, mainly in swamp areas where you just had plants dying, falling in the swamp. Something different about swamps than normal lakes are swamps are anaerobic. There's not a lot of oxygen in there because there's not a lot of stirring up of the water. There's a lot less, there's biological activity, but the plants kind of take the oxygen out. And so it's anaerobic. So when they fall down into the swamps, they don't decompose. They kind of stay like they are. This is a crazy off-topic thing, but has anybody ever seen the swamp log hunter show on the History Channel? They go in the swamps. He's nodding his head yes a little bit. They go in the swamps and they find these old, like huge tree trunks that have essentially been petrified. They've been down there for hundreds of years and not decayed. And they pull them out with big like contraptions, and they cut them up and use them for really expensive wood. They actually make a pretty good living off of it. That's the environment that got us our coals and our petroleum and natural gas and stuff like that. Because you just have millions upon millions of trees falling into the swamps and staying there undecayed for thousands or hundreds of thousands or millions of years. And then eventually more sediment will pile on top. They get compressed into these nice flat layers. And we might talk about this later. They also have to get cooked. You can't just have them there preserved like they would be a tree like these guys are pulling out. They have to get cooked. And so depending on how cooked they get, you will either get like petroleum, natural gas, or coal. And so if you get into like the petroleum industry, which is what I went to master school for, they very much use the term kitchen, and how long your petroleum organic products have been in the kitchen and what like cooked level they're to, because there's a big difference between drilling a well and trying to get petroleum. Petroleum's obviously going to be more expensive. If you drill a well and get natural gas, you might get some money off of it, but you have to do it pretty cheaply. And then you drill a well and you get down into coal. And while coal forms a little bit differently than those, you're not going to be able to extract coal from a well. You have to mine it with a mine and big trucks and mining materials. So it's a very different process. And you need to know what you're kind of looking for down there before you start to spend hundreds of millions of dollars to do a well or a mine. So what environment do you think coquina is deposited on? Remember coquina, this isn't the greatest picture. They could have made it bigger. I mean, you have like a whole quarter of a slide over here. You could have enlarged this. It's a bunch of shells. It's just shells like glued together. And so what environment do you think it is? Right from the beach, man. It comes right off the beach. The shells kind of get broken up from the waves just crashing over and over and over. And they get cemented together by either the salt or the calcium carbonate in the ocean waves. They would be slightly underneath the surface. But yeah, this is a beach rock for sure. While a sandstone can also be a beach rock, a sandstone could also be like a desert rock. And so there's different ways that you can form a sandstone. So let's see. This is your chemical and organic side of the sedimentary rock. So remember, the detrital side only has 6 rocks. The chemical organic side has a couple more. There's 2 main categories. What is the composition? Is it calcite, or do you have something else over here? So we're just going to kind of go through these. And actually, this is maybe a little bit different than some of the other ones we use, and maybe different than the one we'll use in the lab. We'll see. And these words are kind of small here. But what we have is crystalline limestone. This is the limestone that you will see around here in Texas, the white rock. It's sometimes got a gray kind of color to it. If you drip acid on this, it will bubble and fizz because it has that calcium carbonate in it. And we'll see that in the mineral lab when you look for calcite. You drip acid on it, and it'll tell you if it's calcite or not. So this is crystalline limestone. Microcrystalline limestone is going to feel closer to like your obsidian, almost like a glass, but it's not going to look like black glass. It's going to look kind of like this light brown kind of gray color. This would be what they're talking about with the chert and the jasper and the agate and the flint. That's going to be your microcrystalline calcite. This name is too small for me to read, and it's just outside of my brain. Maybe I'll come back to this in a second. Down here you have your coquina. Here's another type of limestone, but it has fossils in it. So if you see a piece of limestone and you can see like a couple shells in there, not like coquina, which is like 100% shells, but if you have a piece of rock and it's got a couple shells or a couple swirly pieces, or something you can identify as probably a shell, just call it a fossiliferous limestone. Fossiliferous meaning it's got fossils in it. Then you have your chalk, which is going to be really white, pretty crumbly and soft, and will have a really soft texture when you break little pieces off. Here's your chert. So I mentioned chert with the microcrystalline limestone. Very similar textures there. Your limestone is going to fizz in with HCl because it has the calcium carbonate in it. Your chert will not. It's mostly quartz. And so similar textures here, different hardnesses. This will be a little bit softer than your chert actually will. And then down here, rock gypsum and rock salt. So these are going to be your two evaporates. Gypsum is much softer than salt. Gypsum is like a 2.5 on the hardness scale, so you should be able to scratch it with your fingernail or something just a little bit harder. Salt would be a little bit harder, and not in today's day and age. 2020 has killed this for us, but if it's salt, you can lick it, and it will taste like salt. It doesn't matter where it's from. Even John Mabry will tell you it's from the Jurassic age. It tastes like salt. And then down here you have coal. This word in front of the coal, bituminous coal, which means it has a little bit of extra kind of oil content in it. You can just call it coal. You don't have to write out the word bituminous. But there are many different types of coal. We use coal for industrial purposes, so you can bet that they have lots of different gradients of coal, how much energy you would get out of it if you burn it, and kind of how good it is for our purposes. This word is travertine. That's what I was looking for. So your travertine is going to be that calcium carbonate. It should bubble and fizz with the hydrochloric acid. What does that say? Non-clastic, fine to coarse crystalline. Non-clastic microcrystalline. So kind of the same as this microcrystalline calcite, but maybe a little bit bigger crystals, although I don't know that you'd be able to see that. Travertine's another thing, like the jasper and the agate that people carve into little carvings and little rock statues and stuff like that. So yeah, these are your chemical sedimentary rocks. They don't go back to it. So here are your 6 detrital ones. This side's a little bit easier. It's all about grain size. This side is a little bit tougher because it's more about what the rock is made of as opposed to the grain side. So the easy one would be the coquina or the coal. Those look very different than everything else. The rest of it all looks and feels pretty similar. For this top half, you'll be able to drip acid on it and it should bubble and fizz. For the bottom half, you will not, especially with the quartz and the gypsum and the salt. Chalk you should probably be able to identify. It's a little different than everything else, but some things in geology get kind of tough to figure out the difference between them. So they're going to talk about lithification, and we've kind of already talked about it. The 2 main parts of making a sedimentary rock are you need that compaction, you need to press all the sediments together, and then you need to cement them together. And the cementation usually comes from silica, which is quartz. So if you have quartz dissolved in your water, as the water flows through all of your sediments, it will leave quartz behind, kind of gluing the pieces together and making that nice sedimentary rock, or calcite. And you can know if it's calcite because, again, you can drip hydrochloric acid on it and determine if it's calcite or quartz. There is some iron oxide rocks that is common cement. Those are the ones like in the Grand Canyon that you will see they have the nice red color because the iron has oxidized and rusted. So you get that nice red kind of feature to it. Now, in sedimentary rocks, and I kind of drew this on the board the other day when I was talking about it being the history book of Earth's history before we started to write stuff down. Each of these individual layers we call bed or strata. And so that's what they talk about up there. Each of the layers is called bed or strata. It's a characteristic of sedimentary rocks, and the reason is sediments always come loose, right? And you need some sort of water to kind of bind them together, and they need to be pressed flat in your cementation and your compaction. And so gravity is going to do the work for you here. If I pour water out onto the desk, it's going to spread out flat. If I pour sand out onto the desk, it might pile up in a pile. Well, it'll probably pile up in a pile. But leave it long enough, and wind and water and weather are going to kind of smooth everything out. And so, in general, and we'll talk about this later in structure when we get to the structure category. All your sedimentary layers start out flat. That's just the way things work. Gravity will do that to them. If there's a hill, they won't spread out over the hill. They'll all go to the bottom of the hill and get as flat as they can. That's the way that sediments work. So your thickness ranges from microscopic in these beds or strata, very thin, maybe just like an ash layer that's just a couple millimeters thin after an eruption, to really, really thick one, tens of meters or even more. That cliff we saw, the chalk cliff, it might be very difficult to see any beds in that. You could call all of that whole thing one large bed or strata. And the lines in between them, when you go from one bed to another, those mark the end of one episode of sedimentation and the beginning of another. So they're like chapter breaks in a book. So if you have a line in between beds, you're very much like, okay, and this might be too simplistic and too big, but you're like, okay, this was the Jurassic era, then you go to the Cretaceous era. And so these are two different time periods in Earth, and you might have some smaller layers in between, but very much you're separating one stage from another, and they should have different attributes to them and tell you a little bit different parts of Earth's history. Fossils are going to be left behind in your beds. Unfortunately, I've never done a whole lot with fossils. I would like to talk more about fossils in this class. We just don't have a whole bunch of time, and they don't spend a lot of time on it. To be honest, that's like if you're a geology major, that's a whole separate full semester class on paleontology, and probably multiple semester classes. To be fair, it gets more into biology. Like when you're starting to study organisms, you got to look at their features to kind of distinguish between the two. Imagine like doing a class on frogs, where like all the frogs look the same, and you just have to look at like, oh, this one has longer toes, or this one has spots, so it's this kind of frog. That's quickly what you get into with fossils. In fact, I don't have it here, but if anybody would like, I have a really awesome book called, I forget the first person's name, Finnick and Frock, maybe. But these guys wrote this book, and it's North American fossils. And so it's literally like almost any fossil you could find in North America. It's an old book, but it's like a classic that everybody still uses. And if you like to go and hike, and you hike in places where you find fossils, you could pick that book up for pretty cheap. And like, it might take you a little while, maybe 10, 20, 30 minutes, but you can find the exact species of the fossil that you just picked up, looking at details on it, and they describe the details. And it'll tell you like exactly when that organism lived, like the exact time period and the dates. It's actually pretty nice. So fossils obviously give you important clues to ancient environments. They can be used to match up rocks of the same age found in different places. And we will get to that in the geologic history and the dating chapter. When we talk about dating these different layers, you can see, certain animals or dinosaurs only lived for small periods of time, like the T-Rex. If you've got a T-Rex skull over here and a T-Rex skull down there, you know that those two layers were deposited at roughly the same time. So how are sedimentary rocks classified? We got our two categories, detrital or chemical. Detrital is pieces of other rocks. Chemical is rocks that have been dissolved into water. And then how are they made after they've been transformed? Lithification. You have to have the compaction and the cementation to hold them together. Now we get into the final stretch, metamorphic rocks. How much time do we have? Oh, we got to get through this quickly. Metamorphic rocks, as I've mentioned, they've been changed. They've undergone metamorphosis, and they've been changed into something else. And the main feature of that is going to be heat and pressure, elevated temperature and pressure. So they have to be underground. They have to be exposed close to some sort of magma or lava. You don't want them right up in it because they can't get melted. Once they get melted, they go back to lava or magma, and they become another igneous rock. But if they come close to it and they get a lot of heat and pressure, then they can be changed chemically into something else. The main thing that we look for when we talk about metamorphic rocks, is what was the parent rock. The metamorphic rock we called the daughter. The parent rock, the parent rock is the rock that the daughter came from. What was it first? Was it an igneous rock? Was it a sedimentary rock? What was it before it got changed in the process of metamorphism? So, or as a verb, I think it's metamorphosed. Just so you know, I'll use that too. So if your parent rock is a shale, which was a detrital sedimentary rock with very small grains like a mudstone, if it gets metamorphosed into slate. Slate is what we use for roofs sometimes. And so you can see they have similar features, similar colors. They have some planes. It's kind of aligned with the board here, but they have some planes of weakness there. And you can see kind of the same planes of weakness here. The only difference is shale is like a mudstone. It's not too hard. You can crumble it fairly easily. Where slate is actually pretty hard. You can like tap it on the desk. It has a nice ringing sound to it. We use it for roofing material or paving of let's be honest, paving of rich people's their sidewalks and walkways and stuff. Because slate, if you're getting slate put down, you got some extra money. It's going to be a lot more expensive than a normal roof. Here's a granite or granodiorite. So they're kind of combining both of these because they're like, is it diorite? Is it granite? It's kind of hard to tell. So let's call it a granodiorite. When metamorphism happens, all these grains, which were kind of mixed up in all different directions, get squeezed, they align vertically, and they kind of segregate themselves. The darker minerals come together, the lighter minerals come together, and you get these nice tiger stripes. If you see these in a rock, or if you have like a countertop that has these black and white stripes in it, that is a metamorphic rock and not actually a granite countertop. And so these are actually really nice. We'll see some rocks that have these features in them. And I need to bring my metamorphic rock up here. It's got some of this too. And so basically with metamorphic rocks, when you heat and pressurize it, you get alignment of your minerals a little bit more. This was already aligned a little bit. It gets better as a metamorphic rock. This was not aligned at all. It gets better as a metamorphic rock. And so this is called foliation. Like foliage from a tree is a flat leaf, or a portfolio are pages in a book that you have made. Foliations are flat, paper-like kind of alignment of your minerals. So there's two different types of metamorphism. There's contact or thermal when you get close to the lava or magma and it heats it up and pressurizes it. Or there's the big regional metamorphism where essentially you get high temperature during mountain building because you're being smushed in between two continental plates that are smashing together. So this makes a lot of metamorphic rocks. This makes it only in small little bands right next to where the magma or the lava was. So those are your two different types of metamorphism. What are the agents? You need the heat, you need the pressure, really. There you do get different types of stress, and some water can be involved when they say chemically active fluids. Usually they're talking about water. But in general, the two main things are going to be your heat and your pressure. You usually need both of those in some sort of form. So they've already showed us this. The foliation I kind of went over. Before metamorphism, your mineral grains are not really aligned. After metamorphism, they're aligned. So you get this random kind of TV screen fuzzy stuff versus your actual nice like tiger stripes in your metamorphic rock. They talk about foliation a little bit. If you want to check up on this, you can get to it. Oh, and there are some rocks that get metamorphosed that don't have foliation. And so you'll see those real quick. These are your metamorphic rocks. Again, metamorphic rocks, not too bad. Only 6 metamorphic rock names that you have to worry about. And they're all pretty different. So you have slate, which is going to be made from your mudstone or your siltstone or your shale. So this is your parent rock over here. This is your metamorphic rock. They show you the alignment of the grains, and then they give you a couple comments about it. So we have slate, which has a nice ringing sound when you hit it. Phyllite will be really shiny and kind of wavy. It has, we haven't really seen the biotite and the muscovite yet, but it kind of has a biotite or muscovite look, a little bit metallic, a little bit like shiny and wavy, almost like glitter. Schist will just kind of be hard, and I will show y'all a garnet schist where you've had garnets kind of being squeezed out. And that's one of the crazy things that can happen in metamorphose. It gets squeezed so much, just a regular shale, mudstone, or siltstone, which is essentially just mud. You can squeeze it and pressurize it so much, literally like red crystals just get squeezed out of it. That's your garnets coming out of the chemical solution that is your schist. And so if it has little garnets in it, we call it a garnet schist. Then we get to gneiss. The G is silent, so it's like nice. Gneiss has your tiger stripes. It's got the black and white stripes where your minerals are not only aligned, but they separated themselves into dark and light categories. And then your two that are non-foliated, they have this little strip here. These are all foliated. They have some sort of flat features because of the alignment. These two are non-foliated. There are no flat features. And it's essentially marble. You may not have known this. We all know about marble. We use it for statues. And again, because it's a little bit rare, it's more expensive than like a granite countertop. But if you have marble countertops, it's more of like a white stone or marble flooring. So marble's here. Marble comes from limestone or dolomite. So even though it's been metamorphosed, you can drip acid on it and it will do the bubble fizz thing. Quartzite comes from sandstones or a quartz-rich rock. It's going to be very similar to the marble. Does not always have to look a different color. It can also be white. The differences is quartzite will be harder. You should not be able to scratch quartzite with a knife, and it will not fizz with the acid. And so if you're not quite sure whether it's marble or quartzite, drip some acid on it and see if it starts to bubble or not. So they kind of go through these again. We're running out of time, so I don't want to go through these. But if you want to read through them, I think I pretty much said everything that they just said. And boom, we're done. Just in time for the bell to ring. Everybody at home, make sure you go pick up a Where's Waldo book and try to find Waldo today, because that's actually pretty fun. He's always hiding somewhere. I don't know why he just doesn't like stand out in the front. Okay, have a nice day, and we'll probably just watch some videos tomorrow. I think I've got some cool videos I want to show y'all. So see you tomorrow.